We have come to the end of Unit 8, and usually we take a day to review everything that we've done in this unit. A lot of what we did was a lot of fun, and then we had some more of a rigorous derivatives and integrals, a couple of sections that we did as well. So let's take a look back at some of the things we did in the beginning of this unit. Let's write an equation for the line tangent to the graph of this curve at the origin. Okay, so we're given the point, so we don't have to go find the point. Let's find the slope, right? So we're taking the slope of this, and we want to find the slope at the origin. So I'm going to take this curve right? And then we're going to take the derivative of both sides with respect to x. Got to do this implicitly because it's not a y equals equation, right? So the derivative of arctan of anything is 1 over the square of the argument plus 1 times the derivative of the argument. Chain rule, right? Chain rule. So the derivative of the argument is going to be 2 plus 1 dy dx. And the derivative on this side will be 2x minus 2y dy dx. Got to do that implicitly. Now we're going to plug in the point, 0, 0. When we plug in the point, this is 0 now, so this is just a 1 times 2 plus dy dx. So this is just 2 plus dy dx on that side, and it's equal to 0 minus 0, so 0. So dy dx is just a negative 2. Therefore, the equation of the line tangent to that curve at that point will be y minus 0 is equal to negative 2 times x minus 0. So just y is equal to negative 2x. Very good. Let's take a look at this next problem. We've got a function, and we just want to find the derivative at 1/2. So this function, we're going to need to use the quotient rule, right? The quotient rule. So let's come over here and use the quotient rule. We start up on top and take the derivative. Derivative of arctan, 1 over the square of that argument plus 1 times the derivative of the argument because we're using the chain rule, right? So that's the derivative of the numerator. For the quotient rule, we multiply by the denominator minus, now the derivative of the denominator, which is just 1, times leave arctan alone. All divided by the denominator squared. So that is f prime. Now we just need to find f prime at 1/2. So let's carefully plug 1/2 in for x. So when we plug 1/2 in for this x, we'll have 4 times a fourth, which is 1. And 1 over 1 plus 1 is 1/2. So this is 1/2 times 2, which is just 1. So this whole piece is 1 when x is 1/2. And then we have that 1/2 from that x. So that's going to be 1/2 for that piece. Come over here. Arctan of, we're putting 1/2 in for x, so this turns, the argument will be 1. What is arctan of 1? Well, the angle that makes tangent 1 in that first quadrant is pi over 4. So that's pi over 4. All divided by 1/2 squared. To simplify this, I'm going to multiply by 4 over 4. 1/2 times 4 is 2. Pi over 4 times 4 is pi. 1/4 times 4 is 1. So this is just 2 minus pi. So the correct answer here would have been B. Okay, part number 3. Here's the function, just find the derivative. It's arc cosecant. So I know that the derivative will be the negative of the derivative for arc secant, right? So 1 over the absolute value of u, so 3x, times the square root of u squared, 9x squared, minus 1, times the derivative of the argument, right? Because it's chain rule, so we have to multiply by 3. Okay, this 3 can cancel with this 3, so we're left with negative 1 over absolute value x times the square root of 9x squared minus 1, and that answer choice is right there at D. Okay, some integrals. Remember completing the square? I hope so. Okay, the 5 that's on top, I'm just going to move outside of the integral. So that just leaves a 1 dx on top. Let's complete the square here. X squared minus 10x. To complete the square, we take half of negative 10 and then square it. So that's going to be a 25. But we had 28, so we need to add 3 more down here to keep it the same. So this will be dx over, okay, come inside and factor that trinomial, and it'll be a perfect square. X minus 5 squared plus 3. Okay, now this is an arctan, and arctan has the 1 over a out in front. U here is the x minus 5. A here is the square root of 3. Du is just dx, so we don't have to multiply by anything else. So we have 5 times, and now we go to the arctan form. 1 over square root of 3, arctan, x minus 5 over square root of 3, plus c. As a multiple choice answer, they would just move the 5 to that numerator. Number 5. Recognize this is arcsecant, so we're going to come off to the side, do an arcsecant. Arcsecant has 1 over a, and it gets a bonus. It gets the absolute value of u with the over a. Okay? So what is u here? U is going to be 3x. A is going to be 5. Okay? Now, this is u squared, but this is not u. So to make that u, we're going to have to put a 3 right there, right? But we can't just come in and put a 3 right there. We need to put a 3 on the top as well. Now we have u and u squared. All right? Inside here, du is 3 dx. And we just now made that nice for us. So that is our du. Remember with arcsecant, it does that. Okay? So the 5 is just going to be written outside, right? And now we go and do our arcsecant form. So 1 over a, arcsecant, absolute value of u over a plus c. And as a multiple choice answer, they would multiply that 5 in. So this would just be arcsecant of absolute value 3x over 5 plus c. Okay. Number 6. Everything that we did before, we can now put inverse trig functions in too. So here we have g that's defined to be this integral. And we want to find g prime. So we're taking the derivative of this. Hopefully you remember that is the fundamental theorem of calculus. So we're taking the derivative of this integral. Okay? And that's going to be, I didn't say it, but that's going to be g prime of x. Alright? So this is now equal to, alright, let's remember the fundamental theorem. Derivative of the integral, so we start at the top, take the derivative, 2x. Now just plug in x squared for every t in the function. So arc sine negative 1 over x squared minus, now go to the bottom and take the derivative. This is a constant, so when we take the derivative it's just 0 and that whole term zeroes out. So this is g prime of x. Now we need g prime of the square root of 2. So let's plug in square root of 2. So we'll have 2 square root of 2 arc sine of negative 1 over square root of 2 squared is 2. Well, arc sine of negative 1/2 is negative pi over 6. So this reduces to negative pi square root of 2 over 3. That was A. Okay? Next little review type of question is one from our growth and decay. A population of penguins is increasing at a rate proportional to the cube root of the population at any given time. So the rate dp dt is equal to k times the cube root of p. That's going to be our differential equation. And now we're going to solve it using the next information, right? That's how we did these. So I'm going to divide both sides by the cube root of p and multiply dt on both sides and then integrate. Separate and integrate. This is p to the negative 1/3. That's my thought bubble, right? So when we integrate that, we get p to the 2/3 times 3/2. Remember I said I need to see that, okay? On the right-hand side, kt plus c. Ran out of room, so I'm going to come over here. I'm going to multiply both sides by 2/3. When I multiply both sides by 2/3, I get p to the 2/3 is equal to 2/3 times k, which is a constant, so that's still just another constant, plus times t plus c times 2/3, so just another constant there. And this is my general equation. Now I need to use my specifics to find c and k. So the population goes from 27 to 125. So at time 0, there are 27 penguins. Let's use that. It'll help us to find C. So if we put 27 in for P, cube root of 27 is 3. 3 squared is 9. T is 0, so 9 is equal to C. So we get P to the 2/3 is equal to KT plus 9. Now we use the other information to find K. The population went to 125 penguins in 6 years. So at 6 years, we have 125 penguins. So 125, the cube root of 125 is 5, and 5 squared is 25. That will equal K times 6 plus 9. Subtract 9, 16 is equal to k times 6, so k is equal to 8/3. So our equation becomes p to the 2/3 is equal to 8/3 t plus 9. If k is small like that, I'll go ahead and put it in the equation. Otherwise, I will leave it separated. That's fine. Either one is fine. So p is equal to 8/3 t plus 9 all to the 3/2 if we solve that for p. Now let's answer the question, how many penguins are there at 9 years? Well, we're just putting 9 in for t. So that would be 8/3 times 9 plus 9 all to the 3/2. This is enough for our q, so this is a safe stop spot. And even though it's with a calculator, did I ever get my calculator out? No, I really didn't need it this time. Okay? I would just leave it like that. If you can't stand it and want to know how many penguins there are, go ahead and get out your calculator and do it. That's fine. Okay, number 8. Okay, this would be on the no calculator portion. A population of baboons is modeled by a function b of t that satisfies the differential equation this. Okay, with t in years and b of 0, so the initial population is 7. Is this logistic? It is logistic, but it's not quite in the form that we want it, right? Because we need this b coefficient in here to be a -1, and right now it's a -1/20. So we're going to factor out a 1/20, right? When you factor out a 1/20, 2 divided by 1/20 is 2 times 20, so that's 40. Okay, so this becomes 1/200b times 40 minus b, and that is the form that we want it in, right? So what is the long term? Oh, well, let's go ahead and sketch the graph. It'll help us with the questions probably. What's the limiting factor? 40. Okay, so that means half of 40 is our point of inflection. Our initial population is way down here at 7, so the curve looks like this, that's where our concavity changes. Okay, what's the long-term behavior of the population of baboons? They're asking for the limit as time goes to infinity of the population. That's going to 40. At what rate is the population of baboons changing when the number of baboons is increasing the fastest? At what rate is the population changing? So we're looking for dB dt at the point where the number of baboons is increasing the fastest. So at b equals 20. This makes sense, you guys, so be sure to read the question and answer the question, okay? Now, I can go into this equation, or this equation, or even this equation. Either one. They're all good. Pick the one that you want to go into, okay? I think I'm going to go into this equation. No, I think I'm going to go into this equation. If I put b as 20, then 20/10, I'll have 20/10 times 2 minus 20/20, right? That would be a safe stop spot. We can safe stop there. This would be 2 times 2 minus 1, so that would be 2. If they asked for units, it would be baboons per year. For what values of b is the solution curve increasing? B is increasing from b equals 7 to b equals 40. So 7 to 40. Find b as a function of t. All right, here comes our Celtic, right? So b will equal, let's get our equation up here. It's a fraction. Do you remember what goes on top? The limit. The limit goes on top. It's crucial. 1 plus, here's our Celtic, c e to the negative lkt, Celtic, right? Where c is L minus P naught over P naught. Do you remember there are two P naughts? I'm trying to help you remember these formulas. So our C is going to be 40 minus 7 all over 7, which is 33 over 7. So our B is 40 divided by 1 plus 33 over 7 e to the negative. All right, I need L times K. L times K is 40 over 200, which is 4 over 20, or 1/5. So 1/5 t. And that's, we just found b is a function of t. All right. How long does it take the population to reach 35 baboons? Well, I'm going to take my equation I just found and put 35 in for b. Remember, the only way we can find anything about t is to write the equation for b, right? So if they ask how long, we've got to come and find that equation first. Okay? So this is, we're putting 35 in for b. Okay? I'm going to multiply both sides by that denominator and divide both sides by the 35. So we're going to have 1 plus the 33 7e over 7e to the negative t over 5. I'm going to write like that. Is equal to 40 divided by 35. So 8/7. 8/7 minus 7/7 is 1/7. Okay. Multiply both sides by 7 and it's gone. Then I have this. I'm going to divide both sides by that 33. Now I'm going to natural log both sides. Natural log both sides. And now multiply both sides by negative 5. That would be a safe stop spot. Did we get a positive time or a negative time? We got a positive time because natural log of something less than 1 will be negative. This is a negative times a negative, so that worked out. Okay? Okay, that's our little quickie review that I usually do in class. So if you missed it, here it is.